Okay, let's talk about this phrase, mind-reading AI. It immediately brings up these pretty intense sci-fi images, doesn't it?
It really does. You think of movies, secret thoughts being pulled out. There's a natural anxiety there.
Totally. Violating that, final frontier of privacy,
Yep,
your own head.
exactly. And that's why researchers, especially someone like Asmat, the clinical psychologist behind the article we're looking at today, are being really careful with the framing.
Right. This isn't just a tech paper. It's framed clinically. What's the title again?
It's called Mind Captioning, a clinical guide to decoding thought, and it just came out November 7th, 2025.
Mind captioning. Okay, so let's set the mission here. We want to understand the science behind this mind captioning. It's about translating brain scan patterns,
Yeah.
fMRI data, right?
Yep, fMRI. Translating those patterns into, well, short descriptive sentences, sensible ones.
And crucially, the goal here for us and for the researchers, it seems, is understanding, not sparking fear.
Absolutely. And the very first thing the paper stresses, we need to be super clear about this. This is not a truth serum.
Right. Not a general mind reader.
No. They describe it as a very careful, cooperative translation layer between specific neural activity and language.
Cooperative meaning the person has to be participating.
Definitely. The big potential they highlight is restoring communication,
Yeah.
giving a voice back to people who've lost it. It's about connection, not intrusion.
Okay, let's get into the mechanics then. How do you go from this, massive amount of brain activity data, fMRI is noisy, right,
Very noisy, yeah.
to a simple, coherent sentence? The article mentions a two-stage pipeline.
That's the core of it. Think of it less like literally reading thoughts and more like using a very specialized translator. Stage one is the first part of that translation.
So what's happening in stage one?
Okay, so stage one is about getting the meaning. The person is in the fMRI scanner, and they're watching short videos, just brief clips.
Okay, seeing things.
Right. As they watch, the fMRI records their brain activity. Then, a linear model, and this is key, it's trained just for that specific person, takes that brain activity.
The whole brain's activity.
Yeah, the whole brain pattern, and translates it into what they call meaning features, semantic features. Think of them as abstract concepts.
Abstract concepts, not words directly. Where do these features come from? That sounds a bit fuzzy.
It does, but it's actually quite concrete in the model. They
Yeah.
come from a pre-existing, powerful, deep language model. It's called DeBERTa Large.
Ah, one of the big AI language models.
Exactly. DeBERTa already has this vast internal map of how language concepts relate to each other. So stage one basically maps the brain's response pattern onto a specific point in DeBERTa's conceptual map.
I see. So the brain signal isn't turned into English yet. It's turned into a sort of abstract code that an AI understands represents a certain meaning.
You got it. That's stage one. Brain scan to concept code.
Okay. Then stage two must be turning that code into words.
Precisely. Stage two uses a different AI model, RoBERTa Large. This one is good at working with language structure. It takes the concept code from stage one.
The DERTA features.
Right. And it starts generating candidate sentences. It kind of iteratively edits them.
Edits them.
How? It generates a sentence, checks if the meaning of that sentence matches the target concept code from the brain, and then tweaks the sentence until it gets a really good match. The article uses the analogy guided sentence evolution.
Guided sentence evolution. I like that. So it's not just spitting out words that were active. It's building a sentence that fits the meaning.
That's the crucial design choice. It's decoding semantic structure. Who did what to whom, the relationships between things. That's why the output is a readable caption, not just a list of nouns.
That makes sense, because earlier brain decoding stuff was often just identifying single objects, right? Like face or house.
Exactly. They could maybe tell you cat or chasing, but this gets you the whole picture. The dog chased the cat. It understands the grammar, the interaction. That structure is the real breakthrough here.
Which brings us to that jump from just nouns to actual, little stories, narratives.
Yeah, generating full sentences, describing actions, interactions. That's the big step forward. It shows the system is grasping the context, not just isolated bits.
There was that striking example in the source material, something about cliff jumping.
Oh yeah, that was a great one. The subject watched a video of someone jumping, and the system generated, from their brain activity alone, the sentence, "A person jumps over a deep waterfall on a mountain ridge."
Wow, that's incredibly specific. Deep waterfall, mountain ridge.
It is, and the performance metrics back this up. They ran tests where the system had to pick the correct caption for a brain scan out of 100 different options.
Okay, a multiple choice test for the AI.
Sort of, yeah. And it got it right about 50% of the time.
50% out of 100 choices.
Right. Think about that. Pure chance would be 1%.
Wow. Okay, that's not just statistical noise, that's significant.
It's a massive gap. It means the system is genuinely recovering specific information about what the person experienced. It's discriminating that one event from 99 other possibilities.
So this really does feel like moving from a cool science experiment towards something potentially practical, thought to text almost.
That's the feeling, yeah. It's getting closer to that.
Now that's when the person is watching the video. What about memory? Did they test if it works if someone just imagines the video?
They did. And this is where, for me at least, it gets really fascinating from a neuroscience perspective. They trained the system only on brain data from when people were actually seeing the video.
Trained only on perception.
Correct. But then they tested it when people were asked to just recall the videos, mentally replay them.
With their eyes closed, just thinking about it.
Yep. Pure mental imagery.
And did it work?
Amazingly well. The same decoders, the ones trained only on vision, were able to generate accurate sentences from the memory recall data.
Seriously? How accurate?
The top individuals were getting nearly 40% correct in that same 100-choice test, just from recalling the video.
Okay, hold on. That's huge. It suggests the brain is using similar neural codes, like the same language, for seeing something and for remembering it.
That's exactly the implication. It points to this shared underlying semantic representation that both perception and imagery tap into.
That's a big deal for understanding consciousness, memory.
Immense. It gives scientists a tool to potentially probe how memories are stored, maybe even how imagination works, in a more objective way than just asking someone what they're thinking.
And you could look at things like maybe how accurate a memory is compared to the original perception.
Potentially, yes, or how vivid it is. And another really important technical detail they mentioned. The model works on single trials.
Meaning you don't need to average hours of data for one output.
Exactly. You get a reading from one short period of watching or remembering. That's what makes you start thinking about real-world applications.
Like quick check-ins in a clinical setting.
It could be. Or maybe even, down the line, structured dream reporting, perhaps. It opens doors because it's fast enough.
Okay, but this power, this accuracy, it brings us right back to that initial anxiety, the big question everyone asks. Can this thing read my secret thoughts, my abstract ideas, my plans?
Right. And the answer, based on this research and how the tech currently works, is a clear and definite no.
A firm no.
A firm no. Asmat's article is very careful to lay out the limitations, the safeguards. There are basically 4 big ones you need to understand.
Let's hear them. This is crucial for grounding the hype.
Okay, first, the hardware. You need a huge, multi-ton fMRI machine.
Right, not exactly portable.
Not at all. And you need hours of scanning time just to train the decoder for one person initially. Second, it's strictly subject-specific.
Meaning the decoder trained on my brain activity won't work on yours.
Exactly. It's like a custom-made key for a specific neural lock, highly personalized.
Okay, 2 down. What else?
Third, the content it decodes is limited. It's focused on decoding these short, visually grounded experiences, either watching the videos or remembering those specific videos. It's not currently equipped to decipher your abstract inner monologue, your philosophical musings, or, your secret plans.
So it's tied to perception or simple recall of perceived events, not free-floating abstract thought.
Correct. And fourth, related to that, it works best on content similar to what it was trained on. If you train it on videos of animals and landscapes, it's not suddenly going to decode your thoughts about mathematics accurately.
It learns a specific dialect based on the training data.
That's a good way to put it. The paper sums it up. It's a consent-based, subject-specific mapping. You have to be actively participating, and it's tailored just for you. It can't be used covertly.
Okay, those constraints are really important. So with those boundaries clear, let's pivot to the clinical promise. You mentioned restoring communication. Who could this help?
The potential is profound for people with conditions like severe aphasia, where, their thinking and cognition might be intact, but they've lost the ability to produce speech, maybe after a stroke.
Right, they know what they want to say but can't get it out.
Exactly. Or people with locked-in syndrome, where cognition is there, but they have almost no voluntary muscle control.
How is this better than existing brain-computer interfaces, BCIs, that try to do similar things?
Well, here's a really powerful finding from the paper. They showed they could get accurate sentence generation even when they computationally removed the brain activity signals coming from the classical language areas.
Wait, they ignored areas like Broca's and Wernicke's, the main speech centers?
Yeah, the areas often damaged in aphasia. And it still worked.
How?
It suggests this mind captioning technique is tapping into that deeper semantic level before it gets translated into motor commands for speech. It's reading the intent, the meaning itself.
So many current BCIs rely on detecting motor intentions, like trying to move a cursor or spell things out.
Right. And those rely on intact motor pathways, which can degrade in progressive diseases like ALS. This semantic route offers a completely different pathway to communication.
A pathway that might be more robust for some patients long term, that's potentially life-changing.
It really is. But with that power comes huge ethical responsibility,
Yeah,
obviously.
absolutely. The article talks about needing an ethical framework, AI governance for mental privacy. What does that look like?
The core principles have to be transparency, consent, and control. Always. No scanning without explicit, informed consent every single time.
Not just a one-off agreement.
No. And clear rules about how the data can be used later. Secondary use needs strict limits. Independent oversight is also crucial. Someone needs to check the models, the data sets, make sure things aren't drifting or developing weird biases.
And recognizing the output isn't pure thought.
Exactly. That's fundamental. The output is an interpretation. It reflects the brain signals, yes, but also the assumptions and biases baked into the AI models used for decoding and generation. The author used a great phrase. All translators carry an accent.
I like that. The AI brings its own accent to the translation, so the output needs careful interpretation.
Definitely. It's an interface, not a direct transcript. Patient agency and understanding that interpretive layer are paramount.
Okay, looking forward then. The article touches on open questions this tech helps explore. What about something like aphantasia?
Right, aphantasia, where people report not having a mind's eye, no vivid mental imagery. Usually it's studied just by asking people.
Subjective reports.
Yeah. But since this mind captioning seems to rely more on the underlying semantic content, not necessarily the vividness of the visual experience.
Because it worked even when ignoring visual cortex signals sometimes, or during recall.
Well, it relies on the shared semantic codes between seeing and recalling. The idea is maybe it could still work for people with aphantasia. It might give us a neural marker, something objective, rather than just relying on questionnaires.
A biological basis for understanding aphantasia, potentially. That's fascinating. What about ADHD or attention?
Well, the current system kind of needs stable focus during the recall or viewing periods to get a clear signal. But you could imagine future versions using shorter time windows, maybe adding a confidence score to the output.
To see how stable the thought pattern is.
Exactly. It could potentially map those quick shifts in attention, giving us a richer picture of different attention profiles, again, grounded in neural data. The flexibility comes from decoding that abstract meaning layer.
This has been, well, a really insightful look into this article and the technology. It walks such a fine line.
It really does. I think the main takeaway is that mind captioning, as it stands and as envisioned by these researchers, is meant as a cooperative tool, a bridge for connection.
Built on active participation and consent.
Absolutely. The ethics have to stay front and center, focusing on patient control, ensuring it empowers, not exposes.
And that final thought from the article really sticks with you, the ultimate goal being simply use mind-reading AI to give people their words back.
It's a powerful, hopeful vision for the technology.
If you want to dig into the specifics, the models, the data, the primary source again is mind captioning, evolving descriptive text of mental content from human brain activity. It was published in Science Advances on November 5, 2025.
Definitely worth a read if you're interested in the technical details.
And it leaves you thinking, if the brain uses such similar codes for seeing and remembering, what does that really tell us about how solid or maybe how malleable our own memories actually are? Something to chew on.